Imagine a multi-ton industrial crane lowering a massive iron shipping container. It needs to stop dead in exactly 2 seconds. If you simply cut the electrical power, the sheer momentum of that load will rip the mechanical components of the crane apart. Controlling that electromechanical violence without destroying the equipment is exactly what the Siemens G120 drive is engineered to do. The system is built from 3 distinct modules. First is the power module, which takes the brunt of the extreme electrical current required to move heavy machinery. Second is the control unit, which acts as the mathematical brain. And finally, the operator panel, giving engineers a direct interface to the logic. Safely halting a multi-ton load requires translating raw physical forces into a precise, real-time software model. Before any calculations happen, the physical installation dictates the drive's survival. The hardware must be mounted in a strict vertical orientation. Engineers are required to leave exactly 100 millimeters of empty space above and below the unit. In a crowded factory cabinet, that is a vast amount of valuable real estate. This diagram illustrates why that space is mandatory. The internal power transistors processing high currents generate extreme heat that naturally rises. That 100 millimeter gap provides a reserve for natural convection, allowing the internal cooling fans to pull in clean air and push the heat away. If you stack these drives directly on top of each other, the upper drive will ingest the superheated exhaust. The cooling system will immediately fail, triggering a thermal overload that trips the drive offline entirely. The physical layout inside an electrical cabinet is a strict calculation to prevent a cascading thermal failure. Moving to the mechanical assembly, the control unit mounts directly onto the power module. During this process, you must hear a distinct click. That sound confirms the establishment and the protective earth, or PE connection, between the 2 modules. Without that connection, a short circuit will bypass the ground entirely. The fault current will electrify the drive's metal chassis, creating a lethal hazard for technicians on the floor. There is also an invisible environmental threat to manage. Heavy motors and high-voltage cables generate dense clouds of electromagnetic noise. To protect the logic, a shield plate is required at the bottom of the unit. This plate acts like a lightning rod, routing the electromagnetic interference safely into the ground and away from the sensitive low-voltage control signals. Mechanical assembly ensures the processor survives both physical, electrical faults and magnetic interference. Next comes the electrical routing. 3-phase power enters the power module, and modulated power drives the motor. This brings us back to our deceleration problem. When the drive commands a massive, fast-spinning motor to stop instantly, the electrical flow changes. Following the law of conservation of energy, that immense physical momentum transforms the motor into a generator. Look at this graph. As the motor's kinetic energy drops towards zero, all that generative power forces a massive spike of electrical energy backward into the drive's DC link. If that voltage climbs unabated, the drive's internal capacitors will literally explode. The engineering solution to this surge is an external braking resistor, wired directly to the drive's R1 and R2 terminals. The resistor absorbs and redirects that lethal DC spike, dissipating the excess electrical energy into the surrounding air as extreme heat. Rapid braking requires converting massive kinetic energy into manageable thermal energy, protecting the internal electronics from catastrophic failure. With the hardware secured, the drive is configured via software using TIA portal or operator panels. The baseline control mode is V/F, or voltage by frequency. It relies on a simple linear relationship, working perfectly for basic fans or pumps. But V/F fails entirely when a multi-ton load requires maximum torque from a dead stop at exactly 0 RPM. To solve the 0 RPM problem, the G120 relies on an advanced mathematical model known as vector control. This diagram shows how vector control mathematically divides the incoming motor current into 2 orthogonal vectors. One creates the magnetic field, and the other produces rotational torque. By decoupling these variables, the drive can scale the torque current up independently of the magnetizing current, delivering maximum rotational force even at a complete standstill. Defeating massive physical inertia requires shifting from basic electrical switching to complex, real-time vector mathematics. This mathematical model cannot function without precise real-world baseline data, and the standard numbers stamped on a motor's nameplate are not detailed enough. The drive must interrogate the motor directly to map its exact physical properties, using a sequence called the motor ID run. The first phase is the stationary ID run. The drive injects direct current into the system without actually spinning the motor. This allows the software to measure the physical resistance of the copper stator windings, accounting for variations in temperature and cable length. The second phase is the rotating ID run. The motor is actively spun so the drive can calculate magnetic flux and leakage inductance. There is a strict engineering rule for this phase. The motor must be entirely decoupled from any belts, gears, or external mechanical loads. External friction and load inertia will pollute the electrical readings. If the motor is weighed down, the drive will calculate corrupted data, resulting in a flawed mathematical model. Once calibrated, the software offers massive advantages over physical rewiring. If the motor spins the wrong direction, an engineer simply changes parameter P1820. This reverses the internal firing sequence of the transistors, completely eliminating the need to physically swap thick, high-voltage cables. A perfect control algorithm relies entirely on pure, uncorrupted data harvested from an isolated mechanical system. Even after a successful commissioning, physical maintenance requires strict adherence to safety protocols, specifically the 5-minute wait rule. In power electronics, cutting the main physical power switch does not instantly render the machine safe to touch. Look at this schematic. Massive internal DC link capacitors act as storage tanks. Even with the power cut, they retain over 600 volts of lethal direct current. That 5-minute wait is the physical duration required for the internal discharge resistors to bleed that lethal voltage down to a survivable level. Touching the electrical terminals before that discharge completes guarantees a severe shock. Industrial safety protocols are dictated entirely by hardware capacitance and physical discharge rates. Pulling back from a single drive, we see the macro architecture of a modern automated factory. Physical on-machine commissioning via an operator panel is being replaced by Profinet communication standards and TIA portal software. Data-driven networks allow engineers to monitor, calibrate, and control entire floors of complex, heavy-duty drives from centralized remote locations. The Siemens G120 drive exemplifies industrial convergence, proving that massive mechanical forces and high-voltage power can be entirely tamed by precision software modeling.